Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. So far in previous videos, we have looked at the theory behind travel demand models, how the travel demand models are set up. So all the videos we have covered so far kind of gives an background of what goes behind developing the model. Now let's say we are working on a project, what we get is the actual travel demand model and we need to know how to use it, what are different characteristics of files we get. So we're gonna look at the use of travel demand models. So assuming that a consultant or agency have already developed their travel demand model using a lot of methods we discussed in past videos. Now what we have received is an actual travel demand model. So let's say we have received travel demand model from MPO. So we have MPO travel demand model and we want to use this model. Now what we need to do is covered under this section. So all the videos under this chapter that are gonna be there, they will cover what to do with this travel demand model, how to use it, how to store it, how to run it, how to play around with this, what to do with these models. So compared to any other traffic operations work where we actually go and build the model, in travel demand model, we don't go and build the model, we receive it from MPOs or the state. So let's look at what to do with this model. So MPO models are generally complex. Proper use of TDM needs an understanding of local TDM model. That's the first statement. The first statement is we need the understanding of local TDM model. Now as an example, I was drawing the map of Texas. So let me try to draw it one more time. So let's say we have one travel demand model from Houston called Houston Galveston Area Council, a GAC model. Then we have one model from Austin, which is Campo TDM model. Then we have one travel demand model from Dallas Fort Worth, let's say NCT COG. Assuming that we are receiving the actual travel demand model and not just the output, several agencies have started to give only the output, so they are responsible to run the model. So we just need to coordinate with those MPOs to get the output. However, assuming that we are gonna get those models from MPOs and we are going to run it, and then in San Antonio, I think is LMO, but I may be wrong. So let's say we have different travel demand models. The first statement is the local travel demand models differ from each other. So having a good understanding of Campo model barely does anything if we go to use NCT COG model. Each model is developed with their own knowledge, understanding, local attributes. Each model has so many characteristics that are specific to local that each travel demand model need to be studied and understood individually. So we cannot look at one travel demand model and call it we have fully understood all the travel demand models. Each travel demand model comes with their user guide, and most of the travel demand models are different from each other. So having a local knowledge of travel demand model is must. So if we have work on certain travel demand models, and if we are working for a different MPO, then all of our knowledge will be kind of waste. We will not be able to use our previous knowledge much to work on new travel demand model. We have to relearn a lot of things to work on a new travel demand model. So that's the local nature of travel demand models. They are very complex and very local in nature. Travel demand software is another thing we need to learn. The softwares have different functionalities. So if we are used to Transguide, there are three we discuss: Transguide, Visum, and Cube. Depending on which software is used, travel demand model procedures and a lot of stuff will be different. And then background in travel demand forecasting is also required, which we have covered in previous videos. So out of these three, the background in travel demand forecasting is kind of more universal and easy to obtain, which we have covered in previous videos. However, learning about the software and the local travel demand model, it takes a lot of time and effort. Due to numerous assumptions, approximations, and complexity involved, the travel demand model outputs are known to deviate significantly from actual observation. So the garbage in, garbage out kind of concept. Travel demand model outputs are highly unreliable in most of the cases, and they are unrealistic for most part. So even though travel demand models are calibrated, validated, they are calibrated for a bigger reason. Let's say the entire MPO area. However, when we work on project, we are focused on one small area, and the link outputs might not match the existing counts or might be far away from the what we are expecting. So travel demand models kind of deviate significantly from actual observation, because not everything is captured within the four-step travel demand model. There are many other factors that plays in that are not captured in any of the models, and hence the output of travel demand model is not the final answer. We need to make some adjustments. So travel demand model gives us an output that kinds of guide us towards a right direction, but it's not the right direction itself. This section will describe the procedure to set up and run travel demand model. So that's what we will see in section 3.5.1, model setup, how to set up the model. Then perform various analysis, including benchmarking, which is part of model setup, subarea analysis, calibration, and many other things, and process to process the output to generate future traffic volume. And this will be the last video hopefully on how to process the travel demand model output. So like I mentioned, travel demand model output is barely reliable. So how we can take this output and try to make sense of it so that we can generate the future volume. We cannot just take the output and directly call it done. There is a lot of post processing needed on the output, and we will discuss those in future videos. So in this video, we will focus on model setup and if possible sub-area analysis. So model setup. Local transportation agencies develop their travel demand models. These models are significantly different from each other. Like I mentioned, different agencies have built their model using local knowledge, and the knowledge differs from each MPO to another MPO. So having a good understanding of one MPO travel demand model does not automatically give us a good understanding of travel demand model for other MPO. We need to have that local touch, the local understanding of where the project is located. So this is very important to understand. A user guide is typically needed to set up, run, and use a particular travel demand model. So when we receive this travel demand model, it comes with a user guide, and we need to read through the user guide to see how the model was developed and what we need to do to set up the models. Given that we are doing it for several projects, we only have to read it for the first few projects, and then we should kind of remember those guides. The user guide contains file and folder structure. So one thing about travel demand model compared to other traffic operation softwares are TDM consists of a lot of files, a lot of files and folders. It can easily be in like 30 to 50 lot of files and folders. So when we are working with travel demand model, our mind can go crazy on how many files and folders are there for one single run. So the user guide contains files and folder structure information, field description. Field descriptions are the attributes I was talking about for zones and roadway attributes. So in zone, there in previous example we were saying there were 50 attributes. Those attributes, like what does those attribute means, and then there are roadway links, and then attributes related to the roadways. So these attributes are coded using certain code. Uh, for example, travel time is coded as TT. A number of household is coded as HH. Household size is coded as HS. So what does this letter represent and what do they mean is defined in this field description. And various options and procedures related to the travel demand model. The model uh, this is another important point, but this is related to all the steps that are used in travel demand model. So we will discuss various option and procedure as they fit relevant in the context. The model in Transcat consists of two different parts. One is file, one is code. Okay. So when we receive the travel demand models, there are some files, uh, or I should call it folder. So there are some files and there are some code. The first step we need to do is compile the code to get the model running. So first thing we do is compile the code. Compile, and the instruction is given usually in user manual. So code is typically written in .src file, which is a GISDK file. So is written here. I think let's look at this point one first. A large number of files are used in travel demand models. Travel demand models must be set up in a particular format where exact folder and file name are provided in user guide. So travel demand models are typically saved on C drive for faster processing. Like we saw in last videos, the travel demand model can easily take 3 days to run. So it's always important to not save them on network drive. Typically, user guidance will ask us on which drive to save on, and typically it's C drive. We cannot go and save it in D drive and let it work. We must follow the instructions for the drive, file name, folder name, and path. So usually it's saved on C drive, and then model name. Let's say I'm working on Campo model, then the C drive / Campo, and then name and year usually is what used. And then there will be substructure of the folders, and the names must be exactly followed as in user guidance. So that's one important thing about model setup. So when we receive the models, we must store it in the specified location. We must rename them or name them with the specified name in the user manual. So that's the first setup of setting up the folder, setting up the files exactly as it is stated in the user guidance. The second one is when we receive the travel demand model, there are files and codes. Like I mentioned, we need to compile the codes, and the codes are can be typically written in GISDK coding format and saved in .src file. So coding in Transcat is done using GISDK script and saved in .src file. A GISDK can be developed and edited using standard text softwares. For example, Notepad. We can just open the files in Notepad and see what is written in there. When more than one .src file is needed, which is typically the case, a list of src file can be written in .lst file. So I'm kind of going through this a lot of kind of descriptions. These are descriptions which we need to understand while running the model. So there are a lot of new words that are coming up. One is .src, next one is .lst. So what I will do is I'll try to explain them, but in the application of travel demand model, there will be a lot of new words that will come in the text. So the first one is .lst file. So .lst file is list all the src file that we want to run. So let's say we have one code for doing trip generation, or one code for skimming, one code for traffic assignment. So there are a bunch um, src. So there are a bunch of src file, and if we want to run all of them at once, we can list them into .lst file and compile the .lst file. So we go ahead and compile a .lst file. Once we compile .lst file, it goes and opens all the src file, not scr, src, which is resource file. It compiles all the src files uh, into a compiler, and then it gives a kind of a executable or kind of a compiled version of these files. It is saved in different files, and the one file which we need to attached to the transcript is .dbd. So after compiling, we will receive a lot of files, and one of these files will have extension of .dbd, which is same extension as the what we had for the roadway network and TAZ layer. So it has dbd extension, and then we go to transcript and attach this dbd compiled file to run those codes. So first we took the codes, then we list them in LST file, then compiled it. Once we compiled it, we got a bunch of files. One of the files will be .dbd file, and then based on user manual, we will attach it to the transcad, and it will run that dbd file, and it will give us the interface to use for a travel demand model. So usually after we run the dbd, we will get the user interface with some buttons and information. So this is a user interface UI, TDM UI, and then there are different steps here. This is how typically we get started with the model setup. This is a side note. GISDK is also used to automate the manual process in Transcad. If we are looking to automate Transcad, GISDK is the way to go. If the manual and repetitive work is needed in Transcad outside of TDM coding, which is already provided, then GISDK script can help reduce the manual effort and avoid errors. Additionally, Excel VBA can be used to run Transcad procedure with varying input iteratively. So this is another important awesome automation technique, is we can write the GISDK script of our own to do certain things over and over and over, and instead of running those GISDK, we can write an Excel VBA that can run those GISDK files. Anything beyond this is kind of out of scope of this book, but this is really helpful, especially when we are working with sub-area analysis or manual traffic assignment, or we are trying to do something where we have to do manually, which is mostly sub-area analysis, and traffic assignment, which is done manually. So traffic assignment is done as a part of model, but sometimes we need to do it manually, and if we are doing it over and over, trying to calibrate, trying to validate, during calibration and validation stage, we have to run the models many times, and we have to attach so many files and play around with so many files. So at that time, this automation becomes very helpful. I have built several automation in GISDK and using VBA to trigger GISDK, but this is a well advanced procedure, so I'll not discuss it here for now. The next step is TDM benchmarking. Like I mentioned, TDM model is very complex. It takes a long time to run, and uh, Here there are steps to set it up. Now how do we know we have set it up correctly? So the TDM output can vary based on Transcat version. So first we need to make sure we are using the exact version that is listed in user manual. So let's say the user manual says use Transcat version 6.4, build build 2, 4, 3, 5, 7. So let's say the guidance says use Transcat 6.4 version and build this. We must exactly use that Transcat version to be able to use this TDM model. TDM models are highly sensitive to what kind of coding that was done in the model. So it's very sensitive to what version we are using. We cannot just use the latest version and switch it to 6.5 or 7 or 8. So whenever we are working with Transcat projects, we usually have multiple versions installed on the computer. So sometimes we might have Transcat 5, 6.1, 6.2, 6.21. Then we might have 7, we might have 8, we might have so many versions installed such that one version is used for one local Transcat model. So Transcat version is very important. Build number, we must exactly match the build number which is given in user manual. And user computer configuration. Sometimes the user computer configuration also changes the output. So we want to make sure that we have set up the model correctly here in model setup, and we have set up the file and folder structure correctly, and then we have done we are using the exact same computer, exact same environment in which model was built. So in order to test this, there is something called benchmarking. Let's look at benchmarking. Benchmarking is running the TDM model and trying to compare the output we receive as consultants output. So this is the output we are generating in our offices as an engineer. So let's say there is consultant C, they generated this output, and one output is already given to us when the TDM model was built. So when TDM model was built, there is an output file or summarized output file, usually in Excel, is given to us with the model. And what we do is we set up all our models, we do all the work, and then we run it, and we do nothing. We just run it and summarize the output. And usually the summary is automatic. So once we run it, the output is summarized. So we are looking at the summary from here, and we are looking for summary from here just to check whether we are producing exact same output as what was produced when the model was developed. Most of the time they do not match actually. So most of the time there is something wrong in the setup. There are so many steps that they will not match, and then we have to go figure out which step did we miss. So the first part is benchmarking. Benchmarking is to verify we are using the TDM model in the environment it was meant to be used. So that's the benchmarking. In order to verify TDM on the user computer has been configured correctly and model benchmarking is done. The original TDM contains the output validation report, which is this part, that are generated while developing the original model. Validation reports contain various tables, summarized outputs, by, um, such as summarized output, link flows by functional class, volume class, etc. These tables are regenerated by running TDM on user computer. So some summary table is given to us with the model, some summary table are generated when we are running the model. Tables from user TDM are compared against tables from original model to verify TDM has been set up correctly. Usually we do it for existing year, but we might have to benchmark future years as well. So usually we just benchmark the base year. Usually benchmarking is done for base year, because we are also trying to see how good our model is performing compared to counts. So usually benchmarking is done for base year, but it can be done for all 3 years, to base year, interim year, and future years. If the summary table is available, to see whether we have set up our base year, interim year, and future year as it was intended. So benchmarking is a very important process. Without doing a proper benchmarking, we can easily mess up the TDM output. The next topic is the study area. Now our model is set up and is ready to use. The first thing we want to do is figure out what is our study area. So let's say this green represents a corridor I'm trying to work on. So usually this is a map in Austin. Let's say this is a freeway we are trying to study. So usually traffic study area are some nearby roadways and the nearby interchanges. So this blue line represents a traffic study area, which is written here. And compared to traffic study area, for the travel demand modeling study area, we consider all the roadways that may potentially influence the volume in the traffic study area. So we consider all the roadway which can potentially vary the traffic, especially along the project limits, but also within the traffic study area. So usually the TDM study area is pretty big, so it's given by this red line. So for a project which looks like this on the roadway, traffic study area will look like this, and TDM study area will look like this red line. This is just a general picturization of how the study area looks like, just to get an idea of how the study area is defined in the travel demand model. This is exactly explained here in travel demand model study area. Next, we will look at something called sub-area analysis. We will quickly look at what is sub-area analysis, some of the steps that are needed for sub-area analysis, and then we will end up this video by closing the sub-area analysis. Some of the steps in sub-area analysis will be carried forward to the regular analysis as well, and some of the regular analysis will be used in sub-area analysis. So sub-area analysis is done when the travel demand models are too big to run. When travel demand models, like I mentioned, takes 3 days to run. Now if I want to do hit and trials to calibrate this model, let's say I want to run 15 different scenarios, or let's say usually in calibration, once we run something, we don't know whether it's right or wrong until we get the output. So usually we end up running it several times. So let's say from previous experience on projects, I know that I typically have to run 15 times. Now this model run will take approximately 45 days, because the model output from first time is analyzed, and only then we can run the second one. Then we look at the output from second one, then run the third one. Now 45 days of engineering time is a lot of money, and we don't have that much time or money to spend on just running the TDM models. So many times what we do is there's something called sub area analysis. Travel demand model can easily take between 2 to 5 days to complete one entire run. If project anticipates many runs, then sub-area analysis is used to reduce the runtime. Sub-area analysis is not suitable for study area where with transit route, as it complicates the splitting the transit route at boundaries. Sub-area analysis includes the following step. So first thing is, sub-area analysis is not good for a study area with transit route, because transit route has their own trip tables and their own kind of structure, and when we break the network to extract out a smaller sub area, then it kind of messes up the model. So what is sub area analysis? Sub area is a smaller area out of the study area. So let's say the Campo model was this big. This blue line represents the entire Campo model. It's usually bigger than this blue line, and we want to study only this small area, which is represented in red. Now to study this small area which is represented in red, we can run the Campo model, let's say again and again and again, or travel demand model again and again, and we can spend many days just running these big models. Or what we can do is we can extract some useful information within this study area, and then run the model just for this study area, using the parameters that was used to run the original model. So this is sub area analysis. Sub area analysis is definitely as not good or not as accurate as running the full model, but in the interest of time and budget, many times we do sub area analysis. So subarea analysis is not good when there are transit system involved in the study area, because when we extract the sub area out, the transit route may be broken and it causes problem. So first one is defining the boundary. Sub area boundaries are typically same as the TDM study area boundary, so there is no question there. However, care should be taken to ensure that sub area boundaries are not crossing any links that are not present in all model years. This is very important. So this is important point number one. So the um, first aspect of defining sub area boundaries or study area boundaries in general is the boundaries are defined such that all the links that are crossing, let's say this is my study area boundaries, such that all the links that are crossing the boundaries should exist in base year, interim year, and horizon year. We want to make sure that all the links that are a part of my study area boundary or sub area boundary exist in all the model years. If a link if a boundary is crossing a link which is not present in one of the year, then the OD matrix which will generate as sub area OD will have different zone numbers between the years, and then when we are trying to transfer the calibration or transfer any logic between the years, we have to do something called matrix manipulation, and it's extremely difficult and it's not that straightforward. So the first thing we want to do, if it's at all possible, is select all the links. First we want to highlight all the links that are going to change between existing, interim, and future year by selecting link attribute, selecting those links that uh, do not exist in all three. So first we select all the links that do not exist in all three. So let's say one of the link exists in base and interim year but not in horizon year, or some of the links exist in only in horizon year. Then we will select all those links, and then we will carefully draw this study area such that we are not touching any of the selected links. This is very important, and why this is important is explained all the way here. So we will soon see why this is important. This has to do something with the new node creation. Next one is input preparation. In order to extract the um, sub area from the full MPO model, we need three files. The first one is full TDM model OD matrix, which is full OD matrix, and then a .NET file, like we were talking in previous examples at the highway skimming. So .NET file which is described here, .NET file which was described here. These are network files. So under highway skimming part, so what we do is we extract the .NET file that contains link attribute that affect travel time. A common link and the common link attributes that are included in net files are free flow travel time, alpha, beta capacity, and existing counts if available. So if existing counts are available, we also extract them such that we can calibrate the sub area. So what we do is we look at the entire big MPO model, then we extract the .NET file with this information, which includes the link node structure and all the travel time information. Other parameters of sub area analysis, mostly related to traffic assignment, match must match the parameters used in full model traffic assignment. So this is another important statement, and we'll look into it soon. Before that, let's look at, so we need the OD matrix, and we need the .NET file, and we also need a full model roadway network file. So we need a roadway network, we need OD, and we need a net file. So what we do is we run the sub area analysis and draw the sub area, and the model goes and does the assignment and everything, and then it extracts the one sub area out. So first step of sub area analysis within Transcad is when we are running the sub area analysis, the software runs the traffic assignment and figure out what are the link flows, and then it cuts out the sub area and then figure out what are the link flows at the boundary of those sub areas, which we will discuss soon here. So the next important thing we were looking at is the parameters of sub area analysis, which are related to traffic assignment, because sub area analysis uh, is kind of based on traffic assignment. So sub area analysis, the first step is the transcat runs the traffic assignment and then extracts the sub area. So the first important parameter of sub area analysis is we should use the same parameter that full model run uses. So we can get all these parameters from the user guidance. So TDM user guidance contain the information about these traffic parameters. There are a lot of parameters, uh, and we need to like which algorithm to use. So let's say the full model is using biconjugate, then we need to use biconjugate model in sub area. Let's say the full model is using multimodal assignment, then during extraction we need to upload the multimodal OD and do the multimodal assignment. Then we need to look at number of zones that are considered, whether all the zones are considered or certain zones are considered in the OD assignment. So OD zone selection. All this information is provided in TDM user guide, and we need to have this information before we actually start doing the traffic assignment or the sub area analysis. So usually we read the user guide, figure out what are the parameters used in the full model run, and then we use the same full parameters from full model run for the sub area analysis. Next one is network extraction. At the end of input preparation, uh, we run the network extraction part. Before network extraction, the software itself runs the multimodal. Let's say we are running multimodal assignment, so it runs the user equilibrium or the assignment, and the network is filled with volumes and travel time. Now the network is filled with volumes and travel time. What software does it extracts the sub area with new OD pairs and new roadway networks. That process is called network extraction. So sub area links and nodes are extracted using sub area analysis tools within Transcat. The output file contains links and node within the sub area boundary, which is given here. So let's say this is my full TDM model and this is the sub area. So the first step is to run first step as a part of sub area analysis. What software does it assigns the link flow. So it figures out what are the link flows throughout the bigger network based on the parameters we have set up here. So we are trying to set up the parameter which matches the full model run parameters, and then during sub area analysis a traffic assignment, only the last part, traffic assignment. So there are trip generation, trip distribution, mode choice, and traffic assignment. So in the sub area analysis, only the traffic assignment part is run based on the parameters we are selecting. So as a part of sub area analysis, the traffic assignment, once traffic assignment is completed, then the link flows are set in the throughout the model, and then the network is extracted based on this boundary created as sub area boundary. So based on this sub area boundary, we know what is the volume here, what is the volume here, what is the volume here, what is the volume here at the boundaries. So these nodes are called external nodes that are created by cutting the network using the sub area. So when we cut the network using sub area, any link that crosses, let's say there was a link like this. So when we extract the sub area, what would happen is, let's say this is my new sub area. This link will kind of end here because there is nothing outside, and this new node is created to represent anything going outside. This new node is shown in on orange color here, called external node. So sub area creates a bunch of external nodes and external links. So these are sub area links, these are internal nodes which were already there, So this is called sub-area network extraction. Now this, based on the traffic assignment we talked about, this orange external nodes are a part of OD. So what we get is sub-area OD. Sub-area OD. In sub-area OD, these external nodes are treated as this internal nodes. So in sub-area OD, we will have this internal nodes. These are internal nodes. And then we will also have external nodes, which are just created. In sub-area, like this is my origin, where here we have internal node and then we have external nodes. Now, important thing to remember is the external node OD was not available as a part of initial OD. So initially this orange nodes does not exist in the bigger one. So in the initial bigger OD for the entire TDM model, there was uh, no mention of this new OD. So let's say this ID for this node is 1000 or 10,001. Let's say this node ID is 10,001. This is just created just now as a part of sub area analysis. This 10,001 is does not exist here. So the full model OD does not have this node 10,001. So now we are looking for to create a new OD where there are new nodes to figure out what volumes are gonna be assigned to new nodes in this OD. That's why the assignment was done. So since we know the volume here and where these vehicles are going, we will know what volume will be assigned for these ODs. So that's why the traffic assignment is the first step of sub-area analysis, so that when the new nodes are created, the origin, destination to and from these new nodes are calculated. Now important part which we were discussing here is the sub-area OD should not cross any. Let me reload this. I think I have drawn enough. So the first thing we were discussing is the sub-area boundaries should not cross any links that are not present in on-border layers. So one of the consequences of creating sub-area ODs are these orange dots, and we have to create sub-area ODs for base year, for interim year, and for horizon year separately. So we take all the year models. Let's say we took the base year model, ran it, and we came up with one base year sub area. Then we took the interim year model, then we ran it and got the interim year sub area. Then similarly we will take the horizon year model, run the sub area analysis, and we will get horizon year sub area. Now if this orange dots are not exactly same in all three of them, then what we have to do is called matrix translation. So let's say this is my base area OD, and it has um, let's say this internal nodes. So let's say it has n number of internal nodes and m number of external nodes, which are these orange ones. And this is for my base sub area OD. And let's say I'm looking for the horizon year, and in horizon year this boundary crosses a link. uh, let's say in horizon year we have a link like this, which is not present in existing year. So there will be a new orange here. So uh, number of external node in the orange one will be, let's say there is one extra link, so there is m plus 1. Number of internal nodes will be ni. This is my horizon year sub area OD. Now I have one extra zones which is not accounted for in the existing. So if we are trying to do something here in this base area sub area OD estimation, let's say we are trying to change some of the OD numbers, it's very difficult to transfer them to future year, horizon year sub area OD. So let's say we have this base sub area OD, and we compared it with existing counts. These are my existing counts OD. and then we did some adjustment to this base area. Now we cannot just transfer those adjustments because now we have an extra zone, and sometimes we can manipulate it, but it's very difficult to play around with manipulating ODs. So it's highly recommendable that we do not cross any of the links that are not present in all three of them. So when we are drawing this study area, we have to be extra careful to not cross any link. Let's say we are crossing one link here, one link here. Let me change the color or reload this. So we need to be very careful that this link and 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 this link, all these links are there in all three model years. This link, this link, any link that our study area is crossing must be there in all three model years. Otherwise we will end up doing matrix manipulation, and that's not fun. That's very tricky. It's definitely not fun, and is something we want to avoid at every cost. So a sub area OD matrix, this is what is explained here. Now the sub area flow validation against the full model. So in the full model, we are running trip generation, we are running trip distribution, we are running mode choice, and we are running traffic assignment. So in full model, we are running 4 steps, and then there are many things we are trying to do. However, in sub area, we are only running traffic assignment, and that too on a highway. So naturally, the results coming from sub area assignment will not match the final, not match the original model. So original TDM is not equivalent to sub area. Now, even though they are not exactly same, what we want to make sure that sub area output is kind of close enough to original TDM. That's the idea. So even though we are not running all four numbers for entire system, what we want to make sure is after we are done with sub area analysis and we are getting the link flow outputs, we are still kind of close to the what the full model was doing. So that's the step to make sure after sub area extraction is done, then we want to make sure the link flows in the sub area is matching the link flows from the full model. So far under sub-area analysis, we looked at how to define boundaries, how to prepare the input. So there are 3 input files. One is roadway file, one is full OD matrix for entire TDM model, and one is network file. Then we looked at how to extract the networks. When we extract the network, then external nodes are created and we get sub-area links, sub-area nodes, and then we also get sub-area OD. That's the output of sub-area analysis. We get sub-area links, sub-area nodes, sub-area ODs, and also link flows on these ODs. Now in this step, we are trying to make sure that sub-area link flows are actually similar to the original model kind of link flow. So sub-area link are assigned with equilibrium flow during the previous network extraction step. So during previous step, link flows are already assigned and given as an output. Sub-area link flows are compared against the full model link flow output. Sub-area link flow output must be close enough. Now close enough is a subjective judgment and depends from project to project, but we'll try to be as close as possible to the full model run link output. If the sub-area link output are not close to the full model run, then the possible cause of discrepancy is explored. Often the discrepancies or error arises because sub-area parameters are not set according to user guidelines. So one of the biggest source of error typically is setting up user equilibrium. So when we are doing sub-area analysis, then then the first step software does is run user equilibrium, and or let's call it traffic assignment. So the first step sub-area analysis runs the traffic assignment, and during the sub-area analysis we have to set the parameters of traffic assignment. which we just talked about few minutes ago. So these parameters of traffic assignments set in the sub-area analysis must match the parameters that is set for full model during typical procedure. So these parameters can be obtained from guidelines, obtained from user guidance. These are embedded within the code, so we cannot go and have a look. We must read the user manual to figure out what are the parameters used and how they are used. Otherwise, we might have to read the GIS script, which is not good. Sub-area calibration. Sub-area calibration is same as the full network calibration, which we will discuss in our future two videos. We will split the calibration into two videos because it's such an important and complex topic for travel demand model calibration. Then coding plan project. So after we are done with the sub-area analysis and we are happy that sub-area analysis output are kind of representing what we want to see, the next step is to code planned projects. So many times some of the projects that are out in the regional plans are not coded in the travel demand model. This step is also used for the full model. It's not only for sub area. So many times some of the projects are missing. Let's say there is a roadway widening, there is going to be a new road which came out after the model was developed. So there are always some network changes that are needed to make for the existing interim and horizon year. So we go and manually code them in the sub area model. And if we are working with full sub area network, and if you are working with full TDM model, then this exact same changes also needs to be made with a full TDM model. If we are using sub area, we need to change sub area. If we are working with full model, we still need to change all, we still need to make this correction in the full model. So coding the planned projects that are not already coded in the roadway network. Then traffic assignment. Sub-area traffic assignment is done using three files. After we have coded the network and then the OD pair, we have already got a sub-area OD as a part of output from sub-area analysis. So we have sub-area OD, we have recoded the network with all the missing information. So we have sub-area OD, we have sub-area net file, sub-area highway, let's say highway scheme file. So let's call it highway net file or highway link node file. So we have sub area OD coming from sub area analysis, which was here, which is this part. Then we have sub area links that includes the planned project, which we just coded in this figure, and .net file. So we have the sub area highway or roadway network, or let's call it sub area link node structure. And then we use the traffic assignment using the OD net file and highway file to calculate the final link flows. So we will get link flows, sub area link flows. Now, important point to remember, like I have been saying several times, that the traffic assignment here must be done using the same parameters that were used using sub area network extraction step. And also the sub area network extraction step parameters were set based on what the full model uses, which is given by user manual, given in manual user manual of the travel demand model. So full model user manual has parameters for traffic assignment that will be used for sub area extraction, that will be used for sub area traffic assignment, and any kind of assignment we are doing. So we need to use the exact same parameters. The output flows provide the new traffic flows on the link, and these traffic flows are further processed manually to generate final traffic volume, and we will discuss this after the calibration videos. So in the next two videos we will discuss how travel demand model is calibrated. It's kind of a little bit long and important topic to see how travel demand models are calibrated. So we will have two videos there, and then one more video on how this model outputs are processed to finalize the final volume. Thank you for listening in, and we will look at the model calibration in the next two videos. Thank you.